Okay, we're going to do some quick review on the whiteboard. I've got a couple of these for you. One of the first and foremost ones, something you've seen before, it's the three-cell model. It really helps describe a lot of why we have the weather we have and why things move in the direction they do. So a couple things to remember. Again, three cells of the three-cell model are the Hadley cell, the Ferrel cell, and the polar cell. Hadley 0 to 30, Ferrel 30 to 60, polar 60 to 90. And they are just the same in the southern hemisphere, so Hadley, Ferrel, polar. So there's actually two Hadley cells in between the Hadley cells for where your equator is going to be. A couple of things to remember always is that the surface winds in the Hadley cell actually flow from north to south, and then they rise and go the opposite direction. So think about that as a surface. That's why weather is generally going to be more predominant in that direction. Ferrel cell, surface winds move north to or south to north. Polar cells, again, north to south. So what happens is, again, so if the Hadley cell, surface winds are moving in this direction, Ferrel cell this direction, and polar cell this direction. Then you throw in the Coriolis force, where you know that everything in the northern hemisphere turns things to the right. So predominantly you have that north to south, but it's going to turn it to the right, so the winds are going to do that. And the Ferrel cell, it's going to turn it to the right, it's going to go in this direction. And the Hadley cell, here. So that's why the Hadley cell, the winds are called the trade winds, are also called, another name for the trade winds is called an easterly wave. And that's the winds that are going to bring hurricanes from east to west across in the trade winds. So those are called the northern trade winds. And the Hadley cell in the southern hemisphere is going to be the same thing. They're going to be coming that direction as well. Ferrel cell, winds are more westerly, the westerlies. And in the polar cell, the polar easterlies. So trade winds, westerlies, easterlies in the polar cells. Couple other fun little names here. Down here you have the intertropical convergence zone, roughly about 10 degrees north or south of the equator. Pretty slow moving air areas where the two Hadley cells will meet, because there's one here as well. Another name for that is also called the doldrums. Sailors used to call that because the winds were so light. Between the Hadley and the Ferrel cell, the horse latitudes, again, areas of, in between the zones are very, at the surface are very slow moving, calm areas. Couple other things, jet streams. There are actually two jet streams in the northern hemisphere. There's what's called the tropical jet here, and then the polar jet here. And we think more about the polar jet because it's what really affects a lot of our weather. Now, they're not necessarily straight lines like most. This is a model. Very zonal wind, meaning very west to east. Zonal means that it's complementing latitude, runs particularly with latitude. But these actually move more in a big giant wave. And I'll do that in red so it's easier to see. So the polar jet's going to run like this, tropical jet like that. They're going to be more south in the winter. But these waves of the jet stream are what are called Rossby waves. So you have your three-cell model, Hadley, Ferrel, polar, know the winds, know the directions, know the junctions in between those, and know the names of Rossby waves. And we'll be getting back in a little bit with a few more tips. Okay, so here's another very recognizable piece of meteorology data, and so it's called the surface station model or surface station model. And picture, if you will, a map of the United States where you have roughly 200 of these plotted about the United States. Those station models, that's where we're reporting their data approximately every 6 hours to put a cumulative data on the weather map. And there's a lot of information, and back in my day, long time ago, that information on a standard map would have to fit inside the size of a dime. So when you're handwriting this, now everything's digital, but a few things you should be able to interpret from this map. And I always reference a clock, so we reference certain symbols as far as the position on a clock. So if this is the center of the clock, so what are some of these numbers again? So here about 10 o'clock, that's going to be temperature, and that's in Fahrenheit. Down here at about 8 o'clock, 7 o'clock is the dew point. And we also know roughly, not perfectly, if you take the dew point and put it over the temperature, it'll give you relative humidity. So 6 to 8's roughly 75%. So right off the bat, we know that here at this model, it's 80 degrees, it's 60%, 60 degrees is the dew point, which means the dew point, if the temperature drops to 60 degrees, that means the air is going to be 100% saturated. Because it's not, it's only 75% saturated. That's the relative humidity. This symbol here at 9 o'clock is the weather. So the different symbols, the two dots, really just mean rain. They're asterisks, they may be snow. They're symbols for thunderstorms, etc., all in there. The center is just basically, what if you went outside and looked up in the air, what would you see? So let's say hypothetically it's filled in 3/4 of the way. That would mean if you went outside and looked up into the sky is 75% covered with clouds, so that's your cloud cover. Here is a wind vane and wind barbs. Wind in meteorology, we use the term is where it's coming from, not where it's going to. So you're going to say the wind is out of the southeast, because that's the way it's pointing. Here's south, here's east, so the wind is a southeast wind. The barbs indicate how strong the wind is. Long barbs are 10 knots, short barbs are 5 knots, so this is going to be 15 knots. Again, and if it's only 5 knots, the barb's going to be like there, it's going to be short of that, so you'd be able to understand if it's long or short if they just don't put it out at the end. Here's pressure trend, so it's a downward line, so that means in the last 3 hours the pressure has been falling steadily. But you may get other symbols where it's like this. It means it's falling and stabilizing, it's rising and flattening out, or it's been stable. So that's what the pressure trend has done. This is how much it's actually fallen in those last 3 hours. And you have to remember, one is to move the decimal point over. So the pressure here has fallen steadily over the last 3 hours, and it's fallen 2.6 millibars in those last 3 hours. Up here is actually the station pressure, which is adjusted to sea level. And again, the average sea level pressure is 1,013.25 millibars. Pressure in North America is generally going to be trending between 1,040 millibars to 980 millibars. So again, here, if you're 986, first thing you have to do is you have to move your decimal point. So now you have a 98.6. And you have to decide, is there going to be a 10 in front of there or a 9 in front of there? If I put a 10 in front of there, that's 10,098. That's way more than that, so that's not a possibility. So pressure here is 998.6, and that's in millibars. So you can get all that information out of that little piece of data. That's a surface station model. So we'll be back with you soon with a couple more tips. Okay. Another pretty common meteorological exercise are plotting isobars. So first, what is an isobar? An isobar is a line of constant pressure. And on a weather map, they are plotted every 4 millibars. So basically, if you started at 1,000 millibars, it would go 1,000, it would go 1,004, 1,008, 1,012, 1,016, if you will. Go in the other direction from 1,000 to 996, 994. Correct? 988, that type of thing. So how do you plot an isobar? Not every station is going to be recorded as a multiple of 4 millibars. So in this exercise, we're going to plot a 1,004 millibar isobar. And everything's already been adjusted, so you're not moving any decimal points. The little dots are actually the station models. So first of all, you can find the 1,004 ones. It's a little bit of a connected dot. So if there's exactly that pressure, you can run the line, the isobar, right through those two models. Now here you're posed with a problem, because here's 1,004, I got to get my line to there, but lines of equal pressure never intersect. So I actually have to go, I know that somewhere between 1,006 and 1,002 there is 1,004. Not really sure where it is, but I know it's in between those two. So I continue on that line. Again, here's 1,006, so I know it's this side of that. It's like a topo map. So I can bring it here to my 1,004. Pretty straight shot up to my next 1,004. Up here again, here's a 6 and a 2, and I know it has to go in, it can't go between here, it can't go over here, it has to go in between those because you know somewhere in between there is 1,004 millibars. I'm turning the corner, here's a 2 and an 8. It's probably a little bit closer to the 2 and the 8 and the contour, so you bring it hug it a little closer, and I can bring it right back there. And that's how you would plot an isobar on a map. A couple other things to look at, again, just I rushed through this a little bit, but again, here's a pressure that's lower than 1,004, here's 1,008, and actually you could actually plot, there might be a 1,000 millibar isobar. Actually, my bad, because you know it has to be inside that. And then here's your actual lowest low, 998, and that's where you're going to put your low pressure symbol. So that's how you plot isobars. Every 4 millibars, connecting the dots, making sure that if it's not on the map, it has to go in between because you know 4 is in between there and between there and there. Hope that helps. Back in a little bit. Okay, quick review on fronts, some other map symbols. Fronts, there are essentially 5 that we talk about. First is a cold front, normally blue. They have little triangles. I like to think of them as icicles. You think of cold. Cold front is the fastest moving front of all of them. And again, as far as direction, the symbols are always on the side that they're going to. So this front is going in this direction. The warm front, very slow moving front. I like to think of them as remember little half sunshine. So warm front, cold front. Excuse me. The occluded front. An occluded front is when a cold front actually catches up to and begins to overtake a warm front. So that's an occluded front. Most rain here, second most rain here. Next one is a stationary front. That's when 2 fronts are lying next to each other. Kind of as a standoff, not one really, they're stalled, if you will, another term for it. So stationary front. And lastly is a dry line front, or also known as a dew point front. Sometimes you'll see it as a brown dotted line. Sometimes you'll see it where it looks similar to a cold front. Symbols, only it's going to be in brown. A dry line front or a dew point front is a front that separates moisture. So maybe not a lot of temperature difference between the 2 sides of the front, if you will. If we got rid of this, it was indicating a front. But maybe it's raining here all over and it's very dry here. So that's why it's called a dry line front. Another couple of symbols are what's called ridges and troughs. A ridge is the highest latitude portion of a high pressure system, and a trough is the lowest portion of a low pressure system. Sometimes you will see on weather maps troughs also marked with a dotted line, and they can be confused with dry line fronts. So fronts, cold front, warm front, occluded front, stationary front, dry line front. Fastest moving, slowest moving, most intense rainstorms, occluded the second most. These you'll probably get long, slow drizzles, not real intense, but kind of linger and hang for a long time. So that's fronts, ridges, and troughs.